Now, on to testing and certification, because I think this is where all of that before has been like, this is how we think about it. Now we want to talk about, so what are we going to do about it? We'll talk about a range of things through this section, but I want to first begin by using this cartoon, because I like to use this cartoon to drive home the basic context for the different levels of interoperability. Right, plug and play with direct communication is inexpensive and quick or timely to implement. Right, it can be done quickly. And it just works. Custom and one-off integrations are time-intensive endeavors. They are expensive, and they constrain innovation and value creation. Right? And it's commonly understood that testing and certification is key to ensuring that plug and play interoperability, right? It's how the Wi-Fi Alliance ensures that all of our devices can communicate with our routers and via, the different Wi-Fi signals, right? So our question is there a way to assure interoperability in the smart grid through testing and certification? So we looked into that question as well. But before we dive into the availability of testing and certification in the smart grid, I want to go back to this concept that we explored earlier, right? Where interoperability allows us to expand asset functionality and impact the grid across multiple scales. So as we think about how interoperability alters the system, we wrestle with the fact that through interoperability, actions that are inherently local can have system-wide impacts, and they're often specifically intended to have a broader effect than the one small action might indicate. So we have to think about the physical context for where actions are performed, right? How these actions are coordinated across application and scale, what communications and interoperability are required, and how to cost-effectively unleash the potential of these devices through standardization across domains. So now let's think about what that means for the interoperability feature space and how standards play into it, right? It gets complicated. Based on what we've just said, we have to acknowledge that physical function, what the actual device can do and what it's intended to do, is a part of interoperability, right? What you're trying to do with a device or system is critical to understanding how we have to communicate about it. So the interoperability profile that you think of would look different for a thermostat or an inverter or a microgrid controller or an electric vehicle. And it may look different for a single device used in two different applications. Then let's consider the communications protocol. So imagine the communications protocol as the envelope in your first class mail, right? It gets your information where it needs to go, and it has some constraints, right? Like you can't ship a Harry Potter novel inside a letter envelope. But within that constraint, you can pretty much get information anywhere you want it to go. And in fact, right, if we take this analogy a bit further, we can say that the difference between the Postal Service and FedEx and UPS and DHL and the large like shipping companies, the object dedicated shipping companies that ship containers around the world, right? This is analogous to the different communications protocols. They each have different purposes, different latencies in their shipping speed, and different capacities in their envelopes or shipping containers. But the information or the data model is different from the communications protocol, but it is equally as important. The information model is what we use to convey the information inside the envelope. It is the language and the grammar and the syntax that allows us to meaningfully communicate with one another. From an interoperability perspective, specifying an envelope without content is just as worthless as specifying the content but not the shipping mechanism. Because if you can't get the information to another device or system, the value of working together simply doesn't exist, right? But the ability, wrong way again, sorry about that. But the ability to combine all of these standards relating to the physical function and the communications protocol and the information model in many different ways, it leads to a combinatorially complex space, which we illustrate here, where each of these clouds represent one potential approach to interoperability. So, given that we understand the need to consider requirements to address the physical function and the data and the information models and the communication protocols, let's look at the landscape of smart grid standards and the availability of testing and certification programs. So NIST did this. We looked at 240 different standards compiled from many different lists. 169 of them were deemed relevant to interoperability. Only about 1 in 5 have third-party testing and certification available, right? Of those, the vast majority were in the communications protocols. So if we were to randomly combine a functional standard with a communication protocol standard with an information model standard, there's less than a 5% chance of having testing certification programs available to cover these three aspects of your system for just this one interface. And now that we know the set of interactions in the system is complex, and we don't seem to have an easy path towards testing and certification to ensure interoperability. And again, we'll use IEEE 1547 as a case study for this issue. Now, as I said before, I love IEEE 1547. I think the evolution of what that standard allows and requires, as we described earlier, drives new capabilities into the grid and is critical for our modernization efforts. But Section 10 of that standard identifies SEP 2.0, DMP3, and Modbus all as acceptable communications protocols to conform with that standard. And it is silent on the required information model. And then, by the way, a footnote in that same section says, and by the way, we really like the 61850 data model. So the interoperability profile space just for IEEE 1547 is therefore complex with a dozen possible implementations. And that creates a somewhat intractable feature space for testing and certification. So let's compare that to California Rule 21, which specifies that the relevant standards and inverter functions. And they have a single communications protocol with a single information model and a set of functions for the inverter function. The resulting testing and certification program, which is UL 1741 SA, I think SA is supplementary amendment or something, but that's where the functions specifically related to California Rule 21 are defined, and the test program is. It is, right, this is a testament to the fact that the implementation clarity brought by California Rule 21 can lead to verifiable testing and certification activities. And so in the framework, we describe the importance of developing interoperability profiles that derive requirements from existing standards, but combine and apply these requirements with a specificity that can provide clarity to industry, stimulate innovation, and hopefully facilitate the introduction of testing certification programs. I want to emphasize, we're not saying new standards are needed. In our landscape analysis, we evaluated 240. We found 169 were relevant to interoperability. New standards are being identified and updated all the time. We're not saying we need a new standard in order to ensure interoperability. What we're saying is that we need to have better specification and specificity within the implementation of the current standards, and to acknowledge that you may draw from one standard for physical function and another standard for communication and another standard for data model, right? And when we combine all that together, by having greater specificity, we hope that implementation will be eased and verification will be facilitated. And we're working with industry to develop interoperability profiles for both electric vehicle charging and inverter-based DER control.